Good morning, dear students. Today we are going to discuss about the very basic principle of interference, which is known as superposition principle. So this is a very familiar principle that you already studied in your plus 2 classes. According to superposition principle, the resultant disturbance due to the superposition of two or more waves at any point at any instant is equal to the algebraic sum of the displacement due to the individual waves. Okay, let me describe this particular principle in a little more detail. Suppose we have two waves, one is this and the other one is this. Okay, and these waves are coming, one is coming from A, the second one is coming from B, and it is meeting at the point R. Okay, so this particular point is the region of crossover. Okay, so one wave is coming from A and the second wave is coming from B, and it is meeting at a point R. Okay, then according to superposition principle, according to this particular statement, suppose from A it is represented as y1, from B the wave is represented as y2. Okay, then according to this particular statement, the resultant displacement R will be equal to y1 plus y2. That is, the resultant displacement at the region of crossover, that is the resultant displacement at this particular point, will be equal to the algebraic sum of, okay, will be equal to the algebraic sum of displacement produced by the individual waves. Okay, y1 is displacement produced by A and y2 is a displacement produced by B. Okay, then according to superposition principle, the resultant displacement R is equal to y1 plus y2 at a particular condition when these y1 and y2 are in phase. Okay, when this y1 and y2 are in phase. The second one is, suppose this y1 and y2 is out of phase. Then what will happen? Then the resultant displacement will be equal to y1 minus y2. Okay. This is the condition where the resultant displacement is equal to y1 plus y2, which is when both the waves are in phase. And this is equal to y1 minus y2 when both the waves are out of phase. Okay. So that is superposition principle. So that is the basic principle and basic statement that you already studied in your higher secondary classes. Now let's describe this principle in details. Let's go a little more mathematical and let's derive the condition for the brightness and darkness. Okay, for that let's consider two waves. Okay, as I mentioned earlier, two waves. Suppose one is coming from A and the other one is coming from B, and it is meeting at a point C or R. Okay, so I'm representing this is A, this is B, and this is the resultant at R. Okay, from A I have y1 and from B I have y2. Okay, from A I have y1 and from B I have y2, and I'm assuming that these two waves, okay, from A and B, I'm assuming that both the sources are coherent sources. Okay, and assuming that from A and B these waves are coherent waves, the first condition is coherent waves. Okay, what is coherence? That we already studied. That is, suppose two waves have same amplitude, same frequency, and it is maintaining a constant phase difference between each other. That is known as coherent waves. Okay, suppose we have a source A and B, it is producing coherent waves. From A it is represented as y1, from B it is represented as y2, and it is producing a resultant displacement at this point R. Okay, and I am assuming that it is both are in phase, so the resultant displacement will be y1 plus y2. Okay, and I am assuming that the second one is both are in phase, so the resultant displacement will be equal to y1 plus y2. Okay. Study this in details, and I am taking, let the y1, the wave from A, is represented as A sin omega t, nothing but a transverse wave with an amplitude A frequency omega. Okay, t is the time. Then y2 is equal to, I told you these are coherent waves. That means these two will be maintaining a constant phase difference between each other. So y2 is equal to, it is having same amplitude, same frequency and a constant phase difference phi between each other. Okay. So these waves are coherent waves. So these having same amplitude, same frequency and maintaining a constant phase difference phi between each other. Okay. So we have the equation here according to superposition principle. The resultant when these two waves are in phase, then it is y1 plus y2. And we have already represented y1 is equal to a sin omega t, y2 is equal to a sin omega t plus phi. So the resultant will be equal to, the r is equal to, instead of y1 I'm replacing a sin omega t plus, for y2 I am replacing a sin omega t plus phi. Okay. For y1 I am replacing as a sin omega t, and for y2 I am replacing as a sin omega t plus phi. Okay. So this is the equation now we have, and here in this term you can see. Okay. So in this term, the second term, there is something called sin omega t plus phi, which is similar to sin A plus B. Okay, sin A plus B, which is equal to sin A cos B plus cos A sin B. Okay, sin A plus B is equal to sin A cos B plus cos A sin B. So let me expand this term. Here A is omega t, B is phi. Okay, so let me expand this term in terms of sin A plus B. So the resultant displacement is equal to, okay, so the resultant displacement is equal to y1 is a sin omega t plus, instead of this thing, that is a sin omega t plus phi, I am expanding like this. Okay, so the equation will become a common sin omega t cos phi plus cos omega t sin phi. Okay, so this will become sin omega t cos phi plus cos omega t sin phi. So the equation now, it is looking like the resultant displacement r is equal to a sin omega t plus a, I am multiplying this, so a sin omega t cos phi plus a cos omega t sin phi. Okay, so here I am expanding this term similar to the like sin A plus B, that is sin A cos B plus cos A sin B. So for more better understanding, let me write here. Okay, A is omega t and B is phi. Okay, so while expanding, we will get sin omega t cos phi plus cos omega t sin phi. Multiplying throughout with a, we'll get a new equation. Okay, so here you can see, here we have a sin omega t, here also we have an a sin omega t. So taking that common terms outside, so the resultant displacement will become a sin omega t, okay, into, here we have only a sin omega t, so 1 plus, here we have cos 1. Okay, so taking that common terms, we will get r is equal to a sin omega t 1 plus cos phi plus a cos omega t sin phi. Okay, that is the equation. Now we simplified this equation, that is the resultant displacement is equal to a sin omega t 1 plus cos phi plus a cos omega t sin phi. Okay, so now let's substitute something, okay, which is a familiar equation. I told you there is, in the previous classes I already mentioned, there is a relation between the phase difference phi and the path difference delta. Okay, there is a relation between phase difference phi and the path difference delta, that is given by phi is equal to 2 pi by lambda into delta. Okay, that is a equation which is connecting the phase difference and path difference. Phi is equal to 2 pi by lambda into delta. So I am going to substitute for phi in the both the equations. Okay, so we will get a pretty big equation, that is the resultant displacement is equal to R is equal to A into sine omega t. Okay, A into sine omega t 1 plus cos, instead of phi we have 2 pi by lambda into delta. 2 pi by lambda into delta plus A cos omega t sine 2 pi by lambda into delta. Okay, so I am substituting for this phase difference phi. So I got another equation, that is the resultant displacement equal to A sin omega t 1 plus cos 2 pi by lambda into delta plus A cos omega t sine 2 pi by lambda into delta. So that is the final equation which we derived. We started from this particular thing, that is we have two waves A and B, which is emitting waves Y1 and Y2, which is in phase and also they are coherent. Okay, they are having same amplitude, same frequency and maintaining a constant phase difference between each other. Okay, so I'm taking that, let us represent light waves. So transverse wave, electromagnetic wave. So I'm representing y1 is equal to A sin omega t and y2 is equal to A sin omega t plus phi, and I'm substituting into the equation principle, that is R is equal to y1 plus y2. I'm substituting here, and in the second term we have something called sin omega t plus phi, which is similar to sin A plus B. So I'm expanding the second term, that is the resultant displacement is equal to A sin omega t plus A common sin omega t cos phi plus cos omega t sin phi. Taking again expanding this thing, we will get the resultant displacement is equal to A sin omega t plus A sin omega t cos phi plus A cos omega t sin phi. Here you can see, here we have an A sin omega t, here also we have an A sin omega t. Taking that common terms outside, so the resultant displacement is A sin omega t into 1 plus cos phi. This is cos phi and here we will get 1. Okay, plus A cos omega t sin phi. Okay, and at this particular point we are applying the relation between the phase difference and the path difference. So phase difference is phi, which is equal to a constant into the path difference delta, that is phi is equal to 2 pi by lambda into delta. So I'm substituting it here. So we got a pretty big equation, which is the final equation of superposition principle. The resultant displacement is equal to the A sin omega t into 1 plus cos 2 pi by lambda into delta plus A cos omega t sin 2 pi by lambda into delta. Now depending on the value of this delta, okay, depending on the value of delta, we will be having the maximum and minimum intensity. Depending on the value of delta, we will be having the maximum and minimum intensity. I hope you understood the topic. Now let's derive the condition for the maximum and minimum intensity. Okay, so for that, in both the cases we need a common equation, right? We already have the equation, that is resultant displacement is equal to A into sine omega t. Okay, resultant displacement is equal to A into sine omega t. Then 1 plus cos 2 pi by lambda into delta plus A into cos omega t sine 2 pi by lambda into delta. Okay, that is the equation we derived earlier. So now we have two cases. One is the constructive interference or brightness. Okay, this is destructive interference or darkness. Okay, to derive that particular thing, we have two conditions for delta. That is the path difference is equal to 0, lambda, 2 lambda, etc. n lambda. That is the first condition I am taking. When delta equal to 0, lambda, 2 lambda, etc. So I am substituting one of these values. So let's taking this delta equal to 0 into this equation. Okay, and I'm substituting delta equal to 0 in this equation. So I'll get the resultant displacement is equal to A into sine omega t. Okay, that is there. 1 plus cos 2 pi by lambda into 0 plus A into cos omega t sine 2 pi by lambda into 0. Okay, so here whatever multiplied with 0 will be 0, right? So the resultant displacement is equal to A into sine omega t 1 plus what is cos 0? 1, right? 1 plus 1 plus A into cos omega t sine 0 is 0. So the resultant displacement is equal to 2A sine omega t. Okay, the resultant displacement is equal to 2A sine omega t. Here the amplitude is 2A, and that is the intensity is proportional to square of the amplitude. Okay, initially the amplitude was A, but now we have a new amplitude which is 2 times the initial amplitude. So the intensity is proportional to square of the amplitude, that is equal to 4A square. Okay, and this is the condition for the constructive interference, or this is the condition for the constructive interference or brightness. So what is the condition for the brightness? Delta is equal to n lambda, n is equal to 0, 1, 2, etc. Okay, delta equal to n lambda is the condition for the constructive interference. Now the second case. Okay, I am taking the second case. Second case, when delta equal to lambda by 2, 3 lambda by 2, etc. 2n plus or minus 1, I am taking 2n minus 1 lambda by 2. Okay, 2n minus 1 lambda by 2 I am taking. Even if it is plus 1, that is fine. Okay, so I am taking delta is equal to lambda by 2, 3 lambda by 2, etc. 2n minus 1 lambda by 2. Okay, so in that case I'm taking the first example. Okay, I'm taking one value out of this, and I'm taking this particular thing and I'm substituting into that equation of resultant displacement. Okay, so I'll be getting the resultant displacement is equal to okay, so I'll be getting the resultant displacement R is equal to A into sine omega t and 1 plus cos 2 pi by lambda into lambda by 2. Okay, instead of delta I have lambda by 2 plus A into cos omega t sine 2 pi by lambda into lambda by 2. Okay, so here let's see, that is here we have lambda cancels. Okay, 2 cancels, lambda cancels, 2 cancels, here also 2 cancels, lambda cancels. So the resultant displacement is equal to A sine omega t 1 plus cos pi plus A cos omega t sine pi. Okay, A sine omega t 1 plus cos pi plus A cos omega t sine pi. What is cos pi? Cos pi is given by, cos pi is minus 1 and sin pi is 0. Okay, so the resultant displacement is equal to A into sine omega t 1 minus 1 plus 0, that is resultant displacement is equal to 0. That is whenever delta is equal to lambda by 2 etc., 3 lambda by 2 etc., 2n minus 1 lambda by 2, that is when delta is equal to 2n minus 1 lambda by 2, we will be getting the resultant displacement is equal to 0. That is, this is the condition for the darkness or the destructive interference. Okay, that is delta equal to 2n minus 1 lambda by 2 is the condition for the destructive interference or darkness. Okay, what we did, we took the final equation and we substituted for delta. Okay, we took the final equation and we substituted for delta. we have two sets of values. First set is delta equal to n lambda. The second set is delta is equal to 2n minus 1 lambda by 2. Okay. Whenever we substitute the first set into this equation, the resultant displacement was equal to 2a something. Okay. The second set, when we substituted, resultant displacement was equal to 0. Okay. So this is the condition for the, when delta equal to n lambda is the condition for the brightness, and delta equal to 2n minus 1 lambda by 2 is the condition for the darkness. Okay. I hope you understood the topic. And okay. Thank you.